In this lecture, we're going to discuss a variant of mathematical induction known as strong induction. And, well, as the name suggests, this is at least going to appear to be a stronger method than the one we've seen in the previous video. At least it should appear that it can prove more statements than just normal induction. It's actually going to turn out that they're completely equivalent, but it's still much more useful to phrase arguments in terms of strong induction sometimes. So we're going to learn that now. So, well, actually, let's first just recall normal induction. So, yeah, the principle of mathematical induction. How does it work? Given statements, or propositions, so propositions for each natural number, propositions indexed by the natural numbers, we're going to do two things. First, we prove the first statement, P1, and that's called the base case. And next, we don't prove anything else directly, but we prove the implication if P of k is true, that implies that the next statement, P of k plus 1, is true. We're not proving P of k is true, we're just assuming it's true, and then we're using that assumption to prove the next one in line. And then that proves a statement for all, so then P of n is true for all n. Okay? So that's the principle of induction. And this is very useful. However, it's sometimes a bit hard to use because of this. So often you get in a situation where the k plus 1 statement seems like it has nothing to do with the k statement. Maybe it seems like it has to do with some earlier statements before k, but it doesn't have to do with the statement right before. And that's actually a common situation. So I'll give an example actually of that. But the solution to that is, so there's a more flexible version. But there's a more flexible version. Which actually turns out to just be the same thing. Or not the same thing, but it's equivalent to the one I already wrote down. But it's called strong induction. Strong induction. So again, you're given statements, propositions, P1, P2. And you start out the same way. So you prove first statement in line. Prove P of 1. I didn't write the name for this second step. It's called the inductive step. So people talk about the inductive step. That's where you're assuming P of k is true and you're proving the next one. So in this one, the inductive step is a little bit different. You're actually going to prove the implication P of 1 and P of 2 and P of 3, etc., all the way up to P of k implies P of k plus 1. Okay, so in other words, assume all of these are true. So i.e., assume all of them. Okay, all the way up to P of k. You have to assume a lot. Then you show that P of k plus 1 is true. Okay, so that's strong induction. And the conclusion is the same. Then P of n is true for all n. So before I get into the details of why these are exactly the same, let's just do an example to show how strong induction works. So here's a really typical case where the first one just doesn't quite cut it. So let's prove that any natural number, remember induction is used for when you're trying to prove statements about any natural number, or every natural number. So prove that any natural number can be written as a product of primes. Very fundamental statement about the natural numbers. And this is actually one half of the fundamental theorem of arithmetic, which is sort of the most important theorem in number theory. It's sort of the foundation of the subject of number theory. That every natural number actually can be written uniquely as a product of primes. There's only one way to do it up to reordering. But here we don't care about unique. We're just proving that we can write any natural number as a product of primes. And how do we do that? Well, we can try induction. So base case, well, we can start with 1. And 1 is, well, you might think, well, wait, 1 is not a prime. So is this really a product of primes? And, well, so mathematicians consider 1 to be sort of the empty product. It's a product that has nothing in it. It's before you start multiplying things into your product. 1 is the default. It's just like 0 is a sum of a bunch of numbers, right? It's a sum of some numbers. It's a sum of exactly no numbers, right? It's just a default starting point when we're talking about sums. So 1 is a default starting point when we're talking about products. So yeah, that's fine. We'll say that works. If you really don't like this, you can do higher base case like 2. But this is totally fine. So this is a product of 0 things, 0 terms. And in the inductive step, we're going to use strong induction. And it's not just to get practice with this. It's actually because we can't use this. And that's because, let's suppose I have a factorization for k into primes. Well, what does that tell me about k plus 1, the factorization for k plus 1? Absolutely nothing, right? So there's not really a way to relate the factorization for one number into primes to the factorization of the next number into primes. That kind of problem is famously difficult in number theory. You're combining addition with factorizations in that way. But strong induction actually is going to work for us. So the inductive step, we will assume that 1, 2, 3, all the way up to k are a product of primes. Okay, every single one of them is a product of primes. And then let's consider k plus 1. So then we'll consider the next number. Well, it might be prime already, right? Maybe we get lucky. So if k plus 1 is prime, we're done, right? It's a product of primes. So not sure what else to say other than we're done. Otherwise, what do? We use the fact that it's not prime to write it as a product of not necessarily primes, but some numbers. So otherwise, k plus 1 is the product of two numbers. How do I know that? And I can even say more about these numbers, a and b. I can say for a and b, well, yeah, natural numbers with a and b strictly greater than 1. They're not equal to 1. It's not just like 1 times k plus 1. And they're both strictly less than k plus 1. right? Because that's what it means to not be prime. Okay, to be prime, it means that you cannot write it as A times B, unless one or the other is number 1. But yeah, there's some non-trivial way to write this as a product of 2 natural numbers. And so we're going to do that. And now we notice that these numbers are smaller than k plus 1. That's where our inductive step is going to kick in, our inductive hypothesis. By the way, that's a word, I'm not sure if I use that yet, but yeah, the first part of this is called the inductive hypothesis. It's the thing you're assuming. Hypothesis. Here it is again. Right, this is my inductive hypothesis there. Assume that everything up to k is a product of primes. Great. Okay, so we've written k as a product of 2 numbers. I don't know that a and b are prime. However, I know that they're both less than k plus 1, which means, let's say by the inductive hypothesis, well, by the thing we're assuming, it's just a fancy way of saying the thing we're assuming, a and b are both themselves products of primes. Okay? All right, that's what we're assuming. Thus it follows for k plus 1. Just take the expressions of a and b and multiply them all together, and you get a big product of primes. Okay? So that's it. Yeah, that's a typical example of strong induction. But you know what I alluded to actually is, so strong induction is actually just totally equivalent. Strong induction and I don't want to call it weak induction really. I'll put it in parentheses. So the one we learned in the previous lecture are just equivalent. Equivalent. And the reason for this is, what's the implication we're trying to prove in weak induction versus strong induction? In weak induction, we're trying to prove P of k implies P of k plus 1. Right? Strong induction, we're trying to show that P of 1 and P of 2 and ... up to P of k all imply, all of those being true implies P of k plus 1. Okay? And so here's something, so let's say I assume this is true. That automatically implies P of k is true, right? So that automatically gives us this implication for weak induction, right? But this seems stronger. So, right? So it's like, why is it that if we assume P of k is true, that's the same as, knowing that all of these are true? And the reason is sort of, it just follows from this principle of induction itself. Because remember, in induction, we're assuming that we have a base case, so P of 1 is true. And then, suppose we know that P of k implies P of k plus 1 for every k. Well, then combine with the base case, right? P of 1 will imply P of 2, which will imply P of 3, which will imply P of 4. So we sort of get all of these for free, right? We get everything up to k just by the principle of induction itself. And so, this being true does actually imply this implication as well. But yeah, just to make it clear, like that, this one follows just from logic, right? If a bunch of statements combine with the AND operator, if this is true, that means that all of these individual ones have to be true, including P of k. This one follows from induction itself, the principle of induction. Okay. But these are equivalent. That doesn't mean you should always use one or the other. Like you shouldn't just use weak induction when the argument really is best phrased in terms of strong induction. Technically, you can do it. It'll just make it way more complicated to phrase. So I would get used to using both of these. And so maybe we should do one more example. We've only done one example so far, so let's do a harder one. So This one's quite tricky, but also interesting and important. So let's prove that any natural number, so any natural number n, has a unique expression. This time we are really going for unique. As not a product this time, but as a sum of distinct powers of 2. And what do I mean exactly by powers of 2? By powers of 2, I mean like well, starting at 1, 2, 4, 8, 16, etc. So these are what I'll consider the powers of 2. So 2 to 0 is allowed, 2 to 1, 2 to 2. But we're not allowing like fractional exponents or negative exponents, things like that. Cool. So prove that any number has a unique expression in terms of these. Just to show what I mean, so like 11 would be, let's see, 2 cubed, 8, plus 1 to 3. So 2 to the 1 plus 2 to the 0. And apparently that's the only way to do it. That's what we're trying to prove. 40, 2 to the 5 plus 2 to the 3, I think. And of course we could have numbers like 64. That's already a power of 2. So that's the unique expression, 2 to the 6. Yeah, there we go. So let's see if we can do it. And we're going to use induction. So proof. And it's not clear whether we need strong induction here, but we might as well default to it because it's not obvious to me how we can get the one for 41 from the one for 40. I mean, it is in this case because we can just add a plus 2 to 0, but we wouldn't be able to get the one for a 12 from this by just adding another one because we're already using it there. But that potentially could work. But let's use we'll use strong induction. So yeah, let's say strong induction. And our base case is always the same. We want to prove it for any n, so we should start our base case at 1. So does 1 have a unique expression in terms of distinct powers of 2? Yeah, I mean, I don't have much to work with, right? It's that. And then the inductive step. Well, so for strong induction, notice how I'm kind of defaulting to strong induction here just because I don't immediately see a way to just get the one for k plus 1 from the expression for k. So I'm going to try to take full advantage of the fact that every number up to k we know is going to have an expression like this. So we'll suppose 1, 2, 3 up to k have unique expressions of this form. I don't want to have to write this out every time. I'll show you later a way that you can avoid writing this out using set notation. Yeah, sums of powers of 2. And again, we want to start by, we're assuming that we want to consider k plus 1, this number. So the number k plus 1. And well, what can we say about k plus 1? I guess taking inspiration from this, so what if it might be a power of 2 already, right? But in this case, we're not quite done. But let's start there maybe. So if k plus 1 is a power of 2, let's give it a name. So let's say k plus 1 is 2 to the m for some m. Well then, great, we have an expression. We need to prove unique, right? We need to prove that that's the only way to write it. But you know that this is essentially going to follow from the fact that if you add up all the powers of 2, like if I add up 1 plus 2 plus 4, I only get 7. I don't even get the next one. I'm one short of the next one. And so that's essentially going to force uniqueness. So how can we actually say that in proof? Well, first, I'll say this expression is unique. This expression must be unique because well, 1 plus 2 plus 4 plus 8 plus etc. all the way up to 2 to the m minus 1. So if I literally use all the other powers of 2 available, it will still only get me to 2 to the m minus 1. And you can use the geometric series formula. By the way, you can also try to prove this using induction, just the regular induction. That's a good exercise, actually. So you want an extra practice problem. Try to prove this formula using induction and not just the geometric series formula. But yeah, because of this, because that formula shows that even if I use all the powers of 2, so even if I use all powers of 2 less than 2 to the m, then 2 to the m, they still cannot sum to k plus 1. Then they still cannot sum, to k plus 1. I guess a good way to say it. Okay, so does that make sense? Not only did I find it, but I proved unique. We have to prove unique in this case, so that's a harder problem. Okay, that's if it is a power of 2. Might need more space, so this will be the last one we'll do in this lecture, but let's try to work through this carefully. So if it is a power of 2, great. This takes care of that case. What if it's not? So if instead k plus 1 is not a power of 2, a power of 2, well, I need to still show that k plus 1 is uniquely expressible as a sum of powers of 2. So we better rely on our induction here. So I need to reduce this down to a smaller case. But again, I don't know what this has to do with the case of k, right? So if it's not a power of 2, well, let's take the biggest power of 2 less than this. And we'll guess that that's included in the arrangement for this. We'll try to confirm that in a bit. But let's guess that the largest power of 2 less than this is going to be included in this arrangement. And the rest of whatever remains after subtracting that off, we can apply our induction. So let's say let 2 to the m now be, let 2 to the m be the largest power of 2 less than k plus 1, right? Less than k plus 1. And then k plus 1 minus that power of 2 minus 2 to the m is well, first of all, this is not a power of 2. This is strictly less. So this is, let's just note, make sure the reader is aware that this number is actually larger than 0. So our induction hypothesis applies. So this is some number larger than 0 and less than k plus 1. So this number is expressible, right? Is expressible as a sum of powers of 2. A unique sum even. A unique sum of distinct powers of 2. Excellent. Here's one possible issue. what if one of those powers of 2 were 2 to the m itself? Well, then my idea of just adding 2 to the m to whatever the expression is here is not going to work because they're no longer going to be distinct. So, but I feel like one of them cannot be 2 to the m. So, and the reason why, so none of which are 2 to the m. And the reason why, so maybe can I do this like parenthetically? So if one of them were, I feel like by kind of the same argument up here, it's not going to work. So if one of them were, then, well, k plus 1 minus that power of 2 is going to be that same power of 2 plus something. So this is going to be greater than 2 to the m. And what this means is k plus 1, if I add the 2 to the m over, is bigger or equal to 2 times 2 to the m, also known as 2 to the m plus 1. That's a contradiction. A contradiction. A little mini proof by contradiction in the middle of this. How about that? So contradiction. Why is that a contradiction? Because that's the largest power of 2 less than k plus 1. 2 to the m, not 2 to the m plus 1. Right? But it's just saying that that's less than k plus m 1. So that's a contradiction. Excellent. Okay. So this is making sense. Well, are there any other issues with this? Potentially, I could have a totally different arrangement for k plus 1. So my arrangement for k plus 1 is going to be 2 to the m plus, so I'll write k plus 1 as, here's my arrangement. There's a power of 2 plus the expression for whatever this number is, which we know exists because of the inductive hypothesis. And we know this does not include a 2 to the m, so all these are distinct. Here's the problem. How do we know these are unique? So you might want to think about that for a second. How do we know there's not a totally different way to write this as a sum of powers of 2? Well, suppose there were. Suppose there were 2 ways to write it. Well, both of them would have to include 2 to the m, right? By the same argument as above. So if there were multiple expressions, both would include 2 to the m, basically for the same reasoning here, right? If they didn't, well, best case they include everything else, but even that doesn't match up to 2 to the m, and this is bigger than 2 to the m. So both are included 2 to the m, and by subtracting 2 to the m from both arrangements, we get, or I said multiple and I said both. So let's just say if there are 2 to make it simple. There might be more, but just pick 2 of them. If there are 2 expressions, so 2 distinct expressions. Both will include that, subtract that, and we get 2 distinct expressions for that number, the one that we used in our inductive hypothesis. But that's a contradiction. A contradiction. Why? Because our inductive hypothesis was that everything up to k have unique expressions as sums of powers of 2. So unique. Right? We want to include that in our hypothesis, because that's really our statement. Right? And so that's it. Yeah. Excellent. Yeah. So I think one thing I promised though is I want to show you that way of writing it using set notation. So here's induction, and then we'll end it. So induction using set notation. So notation version. This was a tough proof, by the way. So it's even tough for me to think through there. So, but yeah, this is the set notation version. So suppose S is a set. So S is some set. And here's induction phrase in terms of set notation. So suppose, first of all, the number 1 is an S. Step 2. So that's my base case. Suppose that K being an S implies K plus 1 is an S. You can modify this if you want the strong induction version. But yeah, this is the weak induction. Then, N being an S, N is an S for all N. This statement, along with the base case, implies N is an S for all natural numbers N. So that's the set notation version. And if you use this instead, when you're phrasing this proof, you can save saying this whole thing. So for example, we basically just did this. So we did the strong induction version, where in our example, S was the set of natural numbers with unique expressions as sums of powers of 2. So you define that at the beginning of your proof, and then you can just refer to S, so being an S. So what does 1 in S mean? It means that 1 has an expression as power of 2. What does K in S mean? It means that K has an expression, a unique expression as sums of distinct powers of 2 even, right? Distinct powers of 2. So that's a way to kind of just save some wordiness here. Okay, well, let's end this lecture here. So I'll see you in the next one.